Very good afternoon and warm welcome to this live session. I'm Dr. Vaibhav Pandit and today we are going to discuss with our students for the topic titled Pseudocolor image processing. So digital image processing is our basic subject we are dealing and this is our 10th live session. So as far as the syllabus is concerned, I have already solved your doubts with respect to the fundamental image processing steps as like the image enhancement, whether it is in the spatial domain or in the frequency domain, and then further the image restoration. After completion of the image enhancements in these two domains and the image restoration, now from the previous session we have started solving your doubts related to the color image processing. So I tell you one thing, the three types of the images we have been learned so far, I hope you are very clear with. The first one is the binary images where only the two shades are there, either complete white as you see on this current digital screen or a complete black. Then we have grayscale images, various shades in between the complete white and complete black we have, and after that we have a switch to the color images here. So in the chapter color image processing, there it is very important topic that we have today to discuss, that it is pseudo color image processing. So with respect to this particular topic, mostly the question into your examination is as like, what is the significance of pseudo color in image processing? Describe the relevant techniques with examples. I tell you people, the application area of pseudocolor image processing is a very wide one here, though you have a very brief introduction and the relevant techniques to your syllabus here. That is why practically learning the concepts of pseudocolor image processing is very important. So first of all, we shall have a look on to the first part of this particular question. What is the significance of pseudocolor in image processing? So as we have pseudocolor for image processing, so we can abbreviate it as PIP here, pseudocolor image processing. So what actually it is done in this particular pseudocolor image processing that we shall see here. First of all, the meaning of the pseudocolor term that it is being used here, the meaning is pseudocolor is called as, or it is nothing but the false color. It is something, the information represented into the false manner, that it is not true here. So by having such the pseudo coloring to the image information what we have here, there it is assignment of the colors, various types of the colors here we have to the gray values based on to a specific criterion. As we used to be dealing with or working with many of the grayscale images into the n-bit environments. For example, the 8-bit environments, we have 2 to the power 8, that means total 256 shades we have. So to the different shades we can have assignment with different colors. The colors may be red, green, orange, blue, yellow and so on, and the different shades in between them as well here. So assigning all such colors to the grayscale values or the intensity values, I hope you are very much familiar with this particular terminology. Intensity values will be the best description of what we are doing in pseudo color image processing. So the meaning of the pseudo color and what way the pseudo color image processing we are having is very important to start with answer to this particular question. Now the next thing to be the answer followed to this particular point should be why this particular term pseudo color is utilized in this type of the image processing. So here we see the term pseudo that just now we have described to be the false color. It is used for differentiation of the process of assigning the colors to the monochrome image. It means the grayscale image from the processes associated with the true color images. In the previous live session we have dealt with the RGB color model. So by using the RGB color model we have the visualization of the total colorfulness with the help of the three bands assigned red, green and blue here. So that particular image processing is somewhat different and this pseudo color image processing is somewhat different. That is why to differentiate by terminology as well, this particular term pseudo color or the false color is utilized here. Yeah, one query is there with the student Prashant Kumar. Which programming language is going to be used? See, right now I am solving the doubts with respect to this. First of all, the conceptual topics, and then I may also take the problems related to the color models, because into the pseudo color image processing, if you see the solution manuals as well, there are no lot of problems associated, but the concepts, the formulation associated are of course there, based on to which the things may come. And as far as the practicals are concerned, which programming language is to be used here, most of the times it is preferred to have the MATLAB. The MATLAB programming is there. In the MATLAB suite you will find the image processing toolbox. So mostly worldwide we have the MATLAB programming. Also you can work out with the images for this particular topic with the help of the Scilab and other open source softwares as well here. So I just continue to the answer of this particular question. So now the pseudo color image processing, the another thing to be following this particular topic should be where it is utilized, because if we don't know the application area where we can best use it and it has a particular significance, then only we shall be having interest in learning this particular technique here. So the answer to this particular is the important and the principal use of this pseudo color image processing for the human visualization is there, and along with we have the interpretation of the grayscale events in an image or the sequence of images here. Now the first part of this particular question, the important one, what is the significance of pseudo color image processing? The answer you can develop with the help of these three points that I have sorted out. The next thing, describe the relevant techniques with the examples here. See, when you check your syllabus, mostly associated to the pseudo color image processing, you will find different applications described in details. But the two simplest techniques here are the intensity slicing, and the next one is the gray level color transformation. If you describe these two techniques which belong to the pseudo color image processing, I think this will be enough here. So here we first of all have the details of the intensity slicing and then the gray level to color transformations here. Now as far as the intensity slicing is there, this is sometimes also referred as the intensity or the density slicing here. So intensity we refer to the particular shade of that particular pixel. The pixel you can specify at particular location into the image plane here. So either you call intensity slicing or density slicing, it is one and the same here. And here to this intensity slicing, the color coding is the very important task here, and the intensity slicing along with this color coding is really very simplest here. Now in this particular case, for the interpretation of the image, here we are dealing now into the color domain. Here we have been switched from the binary to that of the grayscale to that of the color images here. So when we have the color images, we don't describe the image to be only the two-dimensional signal, the two-dimensional information. It is somewhat the three-dimensional information here when we stack together all the different frequency bands that the sensor has individually sensed, and the complete information we can visualize it after combining all those particular image acquisitions here. That is why we can call the image to be a three-dimensional function, and the method that can be viewed as one of the placing planes parallel to the coordinate planes of the image. Each plane will have a slice here for the associated function here. Now for better explanation of this particular point, I can take the help of one illustration. Here we take first of all one horizontal axis, another one is again the axis that is perpendicular to this one but into the horizontal plane, and the third axis which is mutually perpendicular to these two here. So the three axes forms the three-dimensional spatial space, I can say here. So in the plane of the digital screen that you are visualizing, if I have the information that is sensed by certain image acquisition sensor that is confined to a single frequency band from the visual frequency range you can take. For example, if this is for the blue here, this will be one band here. Now along with this band, if we stack with another band information, for example, this is on to the green, and next to that if we have it for the red here. Now you see here the three different bands. The individual bands are there into the plane of the digital screen, and when I stack one plane onto the another and then again another one here, so that you see these planes are arranged onto the third dimensional line that is practically perpendicular to your digital screen. It is coming outwards towards you and inwards inside the digital device here. So that is why we call it to be the three-dimensional function. That is the best suitable description for the color images here, and especially we are going to deal with the pseudo color by the use of intensity slicing here. The description of how exactly the intensity slicing can be made here, or simply you can see here are the three slices you see. One slice is for the red color, another one for the green color, and the next one for the blue color here. Now if you have the image into the grayscale format here, so in the grayscale format, for example, the 8-bit representation here, so you have total 256 shades to describe that particular image information. And when you graphically plot the intensity level of that particular grayscale image information, so that time if you have intersection of the intensity information with a certain horizontal plane, so that will better differentiate the two parts of the intensity information here. So here we describe it. Here we have the illustration. Onto the horizontal axis you see the spatial dimensions denoted by the y on the horizontal one, another horizontal but perpendicular to the digital screen, that it is x. So in between x and y, here you see this is the plane, this is the image plane you can see. So in this image plane you have the information, and for that particular information whatever the intensity level is there or the gray level you see the gray level here it is plotted onto the vertical axis, that it is perpendicular to the image plane. See, this gray level is represented by f here, whereas x and y are correspondingly represented by these two axes which are there into the horizontal plane. So you see the information is having the different levels of intensity at different regions. For example, these two peaks here we have. So to this intensity level, whatever the shaded plane here you see, if we have like this at the particular level marked onto the vertical axis that is intersecting here, so it will differentiate the image information into the two levels. I will moreover say that these are the two levels assigned with two colors here. So onto the upper part, so that portion of the image information that will lie above this particular plane will have color 1 assigned, whereas that particular portion that is lying below the plane will be assigned a different color here. So this way we can have the pseudo color further image processing operations we shall have, and this is with the help of the intensity slicing here. So in the summary I will have certain points here. What we have done, if a different color is assigned to each of the side of the plane, as just now I have shown, any pixel whose gray level is above the plane will be coded with one color and another will be coded with the different color here. Prashant Kumar, your query is color 1 is high pass and color 2 is low pass. Yes, you can compare it with the high pass or low pass filtering here, but as we have this particular intensity slicing, it is one and the same thing. In the high pass and low pass filter, one side we are allowing and another side we are not allowing. We are removing that particular portion. If graphically here we have the plot of the for example say the frequency you see on this horizontal axis. I will have the frequency here, and if you have the filter like this here, so you will allow this much of the frequency range, but you won't allow this much of the range. But what illustration I am here taking, I am allowing both the particular portions of the intensity plotted onto this vertical axis, but with the assignment of different colors. You see here, onto the upper portion I have assigned, here I have mentioned with the red color, and on the downward side here I have mentioned with the blue color. That is the difference. You can compare it to have the understanding, but I am not discarding any of the portion, as it is the case in the for the low pass filtering, or if you take the reverse high pass filtering. Here I am allowing everything here, but with the assignment of different colors, not the same color. If you are working with the grayscale image, it will be somewhat the similar shade. So that is not the case here. We are making this pseudo color assignments here. So I hope you have got my point. Yeah, so I shall proceed here. We had this particular point here. Then the description of the same, what I have discussed here, the result you have seen, the result is now we can describe it to be a two color image here. Next to that, what is the idea for this particular planes? So this is particularly useful for the primary application for the geometric interpretation of the intensity slicing technique. Now the better explanation I can provide you with the help of a more simple figure. Just now what we have discussed for the low pass and high pass types here. So this is what the alternative representation. The alternative representation of the intensity slicing. The earlier illustration we have been taken with the help of the three axis, the three-dimensional illustration you can see. In the two-dimensional illustration, here you see. So whatever the gray levels or intensity levels, generally you refer the terms here. So here it is onto the horizontal axis here, and the color assignment here we have on the vertical axis here. So we have the two levels separated from this particular gray level. Here it is represented small l suffix I. So ith gray level from the range 0 to capital L minus 1. So it has the changes. On the right hand side, we have the assignment of the color that is shown by C2. On the left hand side, we have the assignment of the color shown by C1 here. So I hope the point is clear. This is the simple thing that to understand for the intensity slicing here. So here any input gray level that is assigned one of the two colors depending on whether it is above or below the value of as represented L suffix I here, and if we have the additional labels of the colors to represent for that particular grayscale information here, so that time we can have more stairs in the earlier representation here. So we can also describe this to be the staircase form here. So the illustration of this particular additional color labels we can show you with the help of this particular figure here. So again we have the gray levels on the horizontal axis and the color assignments on the vertical axis. You see the different threshold levels you can have, where you can have the differentiation from one level to another level on the grayscale axis as well, assigned to the different color levels on this color axis I can say you. So this is what the intensity slicing here. So I hope the conceptual understanding of intensity slicing is clear to you people. The practical application can be illustrated. So here we visualize a figure here that has the two parts here, part A and part B here. So in the part A on the left hand side you see there it is a monochrome image of the Picker thyroid phantom. So it is a radiation test pattern you see here. And onto the figure B that is on the right hand side here, here it is the result of intensity slicing of the image in the 8 different colors here. You see here the gradual gray level changes as you find in the right hand side here. So we have the 8 different colors here. So whatever the image that has been acquired by the imaging sensor here, you cannot differentiate a much from whatever information you have recorded here. So when you operate such the input image with the help of the intensity slicing, the 8 different labels if you assign, so you can have the more interpretable image here, and further it can be utilized for the diagnosis purpose. If this is the image from the biomedical image domain, if this is from the satellite platform, we have a lot of applications where we can use this particular information here. Now more information with respect to the input image, which is a peaker thyroid phantom. So the left lobes of the instance here we have, it is, we visualize with the dull gray color in the monochrome image, and the peak out variations into the intensity is quite difficult here. So by contrast, the color image is clearly showing the 8 different regions of the constant intensity. One of each of the colors is used here, and here the intensity slicing assumes a much more meaningful and useful role when subdivision of the grayscale is based on the physical characteristics of the image here. So this information you can add if you have it to be described in your examination. The practically drawing such diagrams is not possible here. Only you can mention the things with these particular points that I have taken from the textbooks, you can note down. So we have another practical example as well to describe the use of the intensity slicing here. So here we have, you can visualize here the X-ray image of the weld here. So here you can see the horizontal dark region that is containing the several cracks and the porosities. Here we have the bright white sticks running horizontally through the middle of the image here, and when there is a porosity or a crack in the weld here, the full strength of the X-rays going through the object saturates the image sensor on the other side of the object here. So if the human were to be the ultimate judge of the analysis and the manual processes were employed to inspect the welds, a simple color coding that assigns one color to the label 255 and another to all the other gray labels will simplify the job that is to be done here. So this is what you see onto the right hand side in the form of figure B here. So what conclusion here we can make? The thermal imaging also works this way, I guess. The Prashant Kumar. Yes, Prashant. You can have the application of this pseudocolor imaging processing in that application also. And Shamin, which class is this? Shamin, this is the class of digital image processing. Generally, it is IP U term for image processing, or you can also have the fundamentals of this particular subject for computer vision subject also. In the electronics and telecommunication, plain electronics, electrical engineering, information technology, computer science, and BTech as well as the MTech level, this particular subject is there. So this is generally for the image processing here. We have it 5th or 6th unit, the color image processing, and the topic here I am dealing with pseudo color image processing here. So I hope the explanation of this particular example that I am dealing to describe the intensity slicing, the first technique to describe the pseudo color image processing is enough. You can have the information in these particular points. If you can reverse my video, you can note down these particular points, or you can have it from textbook as well, but in the textbooks it is quite lengthy portion. I have extracted few of the points here you can get to. Now the third example I can give for this particular intensity slicing and conclude it, and we'll start with the gray level to color transformation, the another technique here. So this is the example of the TRMM. So here TRMM stands for the tropical rainfall measuring mission, that is made with the help of the satellite sensors here. Sensors are mounted onto the satellite platform into the space here, and from there they detect the information here with the help of whatever the reflection they obtain here, and they are designed to detect the rain. A precipitation radar, the microwave imager, and the visible and infrared scanner are the parts of this particular system here, and it is not difficult to generate the grayscale images whose intensity values correspond to the directly to the rainfall here. So this is all to be processed and further passed on to the ground station. The processing, few of the portions are done onto the satellite platform and few of the portion of the processing tasks are completed at the ground station here. So as there are the communication aspects, the memory requirements, that much of bandwidth for communication. So the simple task is to have generation of the grayscale image onto the satellite platform and then send it to the ground station for further application use here. So such the grayscale image that is generated by this particular system here is sent to us with this particular example here we discuss, and we see it into the first part of the image illustration. So here we have total 4 parts, A, B and C, D, you can see here. So we are discussing about the first part, that is the input information here. So this is what the grayscale image that has been generated with the help of this particular system here. Thank you Prashant Kumar for appreciating this lecture. I just continue here. So as along with this particular part A, we have B, C and D also. The visual examination of this particular grayscale picture for the rainfall patterns is quite difficult as we don't have the color differentiation here. And if we have coding after intensity slicing, coding means just assignment of the different colors here. You will get to from part A to that of the part B. Here it is what the colorful image here. But this colorful image is not the naturally existing colorful image. This is the manual assignment of different colors to different intensity levels that we have obtained into the grayscale image here. So though you see this to be the colorful image into the part B, it is not the true color image, but this is the pseudo color image. Our today's topic is pseudo color image processing here, and this image you can best use for differentiation related to whatever the information we gain from different regions of the world here. So I think this is the best example for the intensity slicing technique for achieving the pseudo color image processing here. So I think the 2 points are very clear. The figure part A, the input image, and after intensity slicing, the figure part B here. The assignment of the different colors with respect to the statistics here we have from 0 to less than 20 here. Here it is shown into the figure part C here, and a magnified region. So I think this is for this particular portion. You see it is provided into the part D of this particular illustration here. So the information of these particular 4 parts of this illustration, you can have it for figure part A, B, C and D here. So I suppose the intensity slicing, the first technique is very clear to you people. Now I can shift to the another part, and with the completion of the gray level to color transformation in this particular part, I hope the answer to the question that we are dealing with, we started at initial time here, will be complete here. Prashant Kumar, your question is the color step is arbitrary or we need to follow a certain value here. See here the example is discussed just to illustrate the things in brief here. You can have the assignment of the color at different levels here, and most of the time when the design engineer is working on to such applications, see most limited resources are there for that particular design engineer. So most of the times he will have the trial and error method, assigning different ranges to different colors here, and the visualization what we obtain at the result side here, that is to be judged. So either you can have the juries there, or the design engineer will take the self decision, and having the best visualization obtained for whatever he has been coding thereupon for the assignment of the colors, he will select the best one here. That is only the thing here. And when you shall have the working on to this particular application, while you may be using the MATLAB or the Python, you may be also working with OpenCV, you may also work with. So thereupon you will experience all these particular things. So here we start with the gray level to color transformation. Gray level to color transformation is also one of the technique for pseudo color image processing. Here the approach that is followed for gray level to color transformation, here we can best describe with the help of one figure. Here we have, so on the input side, the left hand side, you see f as a function of x comma y. I hope it is clear. X and y are the spatial dimensions, these are the spatial coordinates you see, and at this particular location with the combined value of x and y, we have the intensity level denoted by f. So clearly f as a function of x comma y is the grayscale image, and as you see the title of this particular technique, this is the input gray level image here. Now to obtain the color transformation, that is the output, that is the right hand side part here, see the three things are made here. To the input image f of x comma y, here we are making the red transformation, then the green transformation and the blue transformation, the corresponding transformations, and further the output bands here we can denote it by f suffix capital R. In the parenthesis you have the usual notation of x comma y here. Then for green, here you have the suffix of capital G to that of f, and for the blue you can denote it by f suffix capital B. In the parenthesis you can have x comma y here. So this is what the general, the basic diagram for gray level to color transformation. We shall definitely discuss in detail. Here we see the idea of this particular gray level to color transformation is to perform the three independent transformations as I have just now shown to you people in this block diagram. The three results are then fed separately to the red, green and blue channels of the color television monitor. So where you are supposed to visualize the results, you are supposed to visualize the results on the screen of the digital device. So most possibly a color television in those days, where the basic textbooks of the image processing as like the Gonzalez or the Anil K. Jain or some others as like the Albovics were written. Yes, I hope these many are the fundamental textbooks for this particular subject here. You can follow it. So this particular method will produce a composite image onto the color television here, and the color content is here modulated by the nature of the transformation functions here. So as this is the new term to you people, what are the transformation functions? In most of the topics of engineering as like the signals and systems, you might have crossed different transformations as like the Fourier transform, Z transform, Laplace transform. Transforms are the mathematical tools. They have a particular criteria with the help of which we can have different types of the representations for the convenient interpretations of the information here. So it is also having the same meaning here. Let us have one example here. So in this particular example, we have the two monochrome images. Monochrome means the grayscale images, and these are for the luggages onto the airport here, and these images are acquired by the X-ray scanning machine here, and the purpose to have this all checking is just to detect whether a person is carrying certain explosive or the banned items or not. So below in the part B and part C here in this particular illustration, you see here it is the part A of the figure, part B of the figure, part C of the figure, and you see the results of the pseudocolor image processing are there onto the part B and part C. Here it is the input image in part A here. Now what are the transformation functions with the help of which we can obtain this particular image from the input and this particular image on this particular input? You can see here. See, the transformation functions are represented graphically here. So this was the information with part A and part B of the figure here. Here you see the first transformation function for the part B of the image here. You see here it is the plot of the three bands red, green and blue, and you see the gray level that is plotted onto the horizontal axis for all these three particular bands, Here it is, the gray level is extending from 0 to capital L minus 1 here, and these are the threshold values to detect the explosives, to detect the garments into the bag here, and whatever the background that it is in the scanning machine here. So this is the first transformation function, and here it is the another transformation function. You just have a change of the range where the explosives and the garments are to be detected in these two transformation functions here. Now these two transformation functions are basically the sinusoidal transformation functions, and they contain the regions of the relatively constant value around the peaks as well as the regions that change rapidly near the valleys here. And changing the phase and frequency of each sinusoid can emphasize in terms of course the color here, color ranges in the grayscale here. So this is what the application here, where the pixels with the gray level values into the steep section of the sinusoids are assigned a much stronger color content as a result of the significant differences between the amplitudes of the three sinusoids caused by the phase displacement between them here. So the image, we have shown you the first part, the input image initially that is scanned, and thereupon we have the pseudocolor image processing to produce the colorful visualization that we have shown you into the part B and part C here. So part B and part C, with the help of the transformation functions I have already shown to you people, the mapping we have made to obtain for the part B and part C here, this allows the observer to see through the contents into this particular luggage here. So whether there are the explosives or not. So this is one of the example here. So in this particular example, it is of the interest to have the combination of the several grayscale or the monochrome images into the single image visualization, which is a colorful visualization here. Now here a frequent use of this particular approach is mostly found in terms of with the cases of the multispectral images here. See, up till now, if we have the information that it is displayed into only one image plane, taking the two dimensions, if this is the image plane, and if we have only two shades, either complete black or white, in this particular image plane region we call it binary. If we have multiple shades, again from complete white to complete dark, we have it to be the grayscale image. And if we have several bands stacked together one below another, so if we have several or the multiple bands, such type of image is called as the multispectral image. Spectra is with respect to a certain frequency range, and to a particular frequency range there it is the visualization of different color, as you see into the 7 colors VibGuire with the help of the experiment you have with that particular device, what is called prism here. When you have the entry of white light from one side onto the another side, we have different 7 colors here. So here it was my point with respect to the multispectral image processing here. The frequent use of this particular approach is found there, and thereupon the different sensors produce the individual grayscale or the monochrome images in each of the different spectral band, as I have discussed here. Here the types of the additional processes, as we see into the figure, here we have the color balancing, the combining images, selecting the 3 different images for the display purpose here, based on to whatever the knowledge of information here we have regarding the response characteristics of the sensors. Also we see this particular block diagram. So initially we had the transformations from the grayscale image to produce the transformed images like the f1 xy to g1 xy, f2 xy to g2 xy, then fk xy in general to gk xy. So the additional processings of the color balancing, the combining of the images, the selecting the 3 different particular images for display purpose here. Here it is shown with the help of the block here, additional processing, and finally here we have the representation in terms of h suffix capital R, capital G, capital B, and the spatial dimensions denoted by x comma Y here. Now here we have another example here. So in this particular example, we have the Washington DC area that is captured with the help of the satellite sensor. Most possibly, I think this is the image of the Landsat satellite here. So from figures A through D, here we have the total 6 parts actually. The first 4 parts we visualize. First one, the band 1 and band 2. Then we visualize the individual band 3 and band 4. Here you see. So the first 4 parts, figures A through D, these show the 4 spectral bands of the images for the Washington DC area. So this includes the Potomac River, the river flowing through that particular region, as you see into the central region here. See, the clarity of this particular river is different from band 1 to band 4 here, and these particular bands as shown into the figure A, B, C and D are correspondingly for the red, green, blue and the near infrared here. So what we had earlier, that it was band 1 and band 2, here we have band 1 for the information sensed when the sensor is confined to the frequency range of the red color only from the electromagnetic spectrum. For band 2, it is for the green here, and for the band 3, here we have for the blue color, and the band 4, here it is for the near infrared. Near infrared is sometimes also abbreviated as NIR here. NIR standing for the near infrared region here. If you check the electromagnetic frequency spectrum diagram here, thereupon you will find the infrared region very close to that of the visual range of the electromagnetic frequencies here. Now after these 4 parts here, for the same Washington DC area, we have the 5th part to visualize here, and this is the representation of the full color information displayed into the image plane here. And this is basically the combination of the first 3 bands, red, green and blue here. So that is why most of the times the full color representation of the image is also said to be the RGB image here. RGB standing for red, green and blue here. And then we have the 6th part, as you see most of the portion red in the right hand side here. It is formed by replacing the red component of the left hand side figure with the near infrared image here. So this is what the visualization here we have obtained on the right hand side. So I hope the example is clear to you people. The points to describe the 4 parts and the next 2 parts we have completed here. So in this particular example, the full color of the image of the dense areas are basically difficult to interpret here, and here we know that the near infrared band is strongly responsive to the biomass components of to the scene. Hence it has been used here to have the visualization at the last portion here, that it is figure F here. So the figure F shows quite clear description of the difference between the biomass into the red color and the human made features as like the buildings and all those into the bluish color here. And this type of processing is quite powerful in helping visualization of the images of the interest into the complex images, especially when those events are beyond our normal sensing capabilities here. Our eye is also one of the imaging sensor here, and we also have a specific frequency range in which only we can have the visualization and the distinction of one object from another into the same scenario here. Now we shall have conclude of this particular topic, gray level to color transformation here, with the help of one more figure here, that is the excellent illustration of whatever the points here we have seen here. So we visualize the 2 parts A and B of the image here. In the part A, we have the pseudocolor rendition of the Jupiter moon 1010 here, and a close-up picture or the magnified view of the same here we see into the part B here. So these 2 are the images of the Jupiter moon 10, and these are shown with the help of the pseudo color. These are not the natural colors. After getting the information sensed at the satellite platform, assignment of different colors to the various ranges of the intensity have been made, and then we have obtained these particular images. And I know that these two images are really very visually appealing images here, and with the help of all such visualization that is best suitable to the human visual system here, we can take the different decisions to process these particular images for further information extraction here. So now, by understanding the physical and chemical processes that likely to affect the sensor response, it is possible to have the combination of the sensed images into a meaningful pseudo-color map, as you see onto the left hand side here. And in this pseudo-color image, the bright red depicts the material that is newly ejected from the active volcano on that particular Jupiter moon, and that is surrounded by the yellow materials which is of the older time here. So you see here on this particular Jupiter moon here, there it is the study of what the things are going for this particular volcano existed here. Whatever the red particular portion here we see, this is the newly ejected material, and whatever the yellowish it is there, so it is of the older time here. This is what the description in this particular image here. So these images are just for the understanding purpose of this particular concept. You can have completion of your answer to what we had there. These are just the points we discussed here. So the question that it was, I just repeat the question. What is the significance of pseudocolor in image processing, and describe the two techniques relevant to it. So the two techniques, intensity slicing and gray level to color transformation, that is also there into the textbook. We have completed into the details here. The points you can note down, and you can develop these particular points to have your answer here. So I hope the things with respect to the pseudocolor image processing are clear to you people. And as we have 10 minutes more, I can have certain more information with respect to the CMY. Along with the CMY, we have the CMYK color model. In the previous live session for the image processing subject, we dealt with the RGB color model. I hope you have a background of it. So RGB, we are standing for the red, green and blue colors here. So what are the C, M and Y? In that live session also, at one of the slide I have discussed is, see here, the C stands for the CAN, CYAN. M stands for the magenta, and Y stands for the yellow here. So these are the CAN, magenta and yellow, the three factors first of all we shall discuss, and into the CMYK, what is K, I will also discuss. The three, CAN, magenta and yellow, these are the secondary colors. Secondary colors. What are the primary colors? The primary colors are, already we have discussed, red, green and blue here. And when it is the time to discuss about the pigments here, the pigments are formed by the combinations of the primary color. You can have the pairs, red with green, green with blue, red with blue. So that way we can have the formation of the pigments, and these are the primary pigments here. So what are CMY? CMY are the primary pigments you say, or the secondary colors you say. These are respectively CAN, magenta and yellow. Now the more information with respect to the CMY can be given with the help of one simple example here. And what is the significance of the CMY into the image processing may also be one of the question to your examination here. So when we have a surface coated with the CAN pigment that is illuminated with the help of the white light, there it is no reflection of the red light component from that particular surface here. So the conclusion what we make, that CAN will subtract the red light from the reflected white light. We shall also see it with the help of the mathematical expression here. And the white light is itself a composition of the equal amount of the primary colors. I say the primary colors are here are red, green and blue here. So these are the primary colors. Whenever you will be asked for this particular chapter, what are the primary colors? So these are the three: red, green and blue. And what are the primary pigments? So these are cyan, magenta and yellow. When asked what are the secondary colors, then cyan, magenta and yellow. So this is what the information with respect to the CMY here. Now one question may be there to your mind, why we are learning the CMY color model or CMYK color model, what is the application area, where it is used. So the answer can be, there are most of the devices that are depositing the colored pigments onto the hard copy or the paper. So these devices are the color printers, the copiers. So these require this CMY color models here. So the key CMY data input is fed to them and they are performing onto the RGB to CMY conversion internally, and they are producing the hard copies into the colorful form here. Now here we require then the conversion RGB to CMY, CMY to RGB, vice versa we can have here. So the basic understanding of this particular conversion is very simple. How to obtain CMY if we have the image information into the RGB form? The thing is very simple. You see here, we subtract the RGB representation from this state particular when we have all the three entities at the level 1 here. We can have these three components individually into the range 0 to 1, or you can regard this particular to be the 100%. For the three individual components, we have all the three to be 100%. From this 100%, when you individually subtract R, G and B, the correspondingly you obtain C, M and Y. So you can obtain CAN. CAN, if you will obtain, it will be just 1 minus red component. So the same thing we have discussed on to the previous slide here. So here again we have the assumption for the range 0 to 1 as just now discussed here. The equation we have demonstrated for the CAN, here we have CAN to be obtained 1 minus red. That is why I had said that there it is no reflection of the red component from the surface where it is there the uniformity of the CAN there. Now the similar is the case. We can also say that you can obtain the pure magenta. You will see the middle term of the matrix equation onto the previous slide. That is the pure magenta that will not reflect the green component. So 1 minus G, and the pure yellow will not reflect the blue component. So Y it will be equal to 1 minus capital B there. So reverse case should also be possible. This conversion we have seen RGB to CMY. RGB to CMY. We can also have CMY to RGB. Yes, Prashant, your question is, can't we use RGB for hard copy? See, the R, G and B, already in my previous session also I have discussed that all these digital devices, just now we have the smartphones, they have very good resolution cameras also fitted. So these cameras are only the mimics of the human visual system we have that has been naturally gifted by God to us here. So how our eye operates, the anatomy of the eye, the working, I have already discussed. My lectures are there on the online platform, you can attend to also. So if you see the internal structure here, there should be certain element to sense the information. So naturally we have our organs into our body. So like that we have eye. So the basic part is a cell. The group of cells form the tissues here. So there are such components what we call cones. So there are the cones, those are sensitive to the red light, to that of the green light and blue light. So these are the prominent cones that are naturally gifted by God to us. That is why our visual system is best suitable for the RGB. But for interpretation, we have to also get the details in terms of HSI also. That later I will also discuss. H standing for the hue, S starting for the saturation, and I starting for the intensity. Intensity you will say, or brightness you will say here. So whenever the design engineers are working on to have design of the digital devices, they are referring to a certain model here. So in the application area of having the hard copies generated through the printers and copiers, so there it is, the RGB to CMY conversion here. So RGB model is best fitted for our visual interpretation here. So I hope you will get my point here. So what I was discussing about, the reverse way, the CMY to RGB here. So the equation we have already discussed how the CMY and RGB are there. We can also have modified form of this particular equation, taking RGB to left hand side and CMY to right hand side. You will obtain the RGB from the CMY values here. So here this equation also reveals that the RGB values can be obtained easily from the set of CMY. Same thing we have to do. We have to subtract these individual components from 1 here. Now in this particular image processing, the color model that we are discussing about, the color model initially we are talking about CMY, later on we shall talk about CMYK here. So the color model is used in connection with generating the hard copy output, as just now we have discussed here. So the inverse operation is of very rare use here, or practically having very little interest here, and the mathematical expression for the conversion, as just now we have discussed, here we can give it to you. So with the help of these equations and discussion, I hope you are well familiar with the C, M and Y, can, magenta and yellow. So what is the K into the second title here? So according to one of the figure that we have already discussed for the color fundamentals before starting the RGB color model, the equal amounts of the pigment primaries. So CMY are the primary pigments, RGB are the primary colors here. So the equal amounts should produce a black color, and the black color, if it is taken additional to have the representation here for the best suitable visualization here, that is basically just a modification of CMY color model to that of CMYK color model here. So this is what the same point we are discussing. Into the practice, we are having the combination of these colors which will generate a muddy looking black color. So if we have the complete blackness to it, so we can have the individual components, the fourth component here. So in the application area, most times the publishers are talking about the 4 color printing. So the fourth color is the black color here. Their devices are having can, magenta, yellow added by the black here. So this is what the CMYK here. Now I will show you one basic illustration. In that particular diagram, you will find all the color components we have been talking throughout this particular chapter. So this is just a color cube here. On the right hand side, I will show you a colorful visualization. You see like this here. So if you have the 3 axes mutually perpendicular into the space, the 3-dimensional space that has been defined like this here. So this is basically the axis coming towards you people and going inside in the background here. So R is the designation of red color here. So in the colorful side, you see here it is the corner or the vertex, you say, that is of the red color here. Then we have G for green here. Here it is green. And here we have capital B to denote the blue color. You can also denote it with the help of the coordinate values in the 3-dimensional space with the help of the rectangular coordinate axis here. So you see blue color at this particular vertex here, red color here, and the green color here. So when you take the combinations of these primary colors, you will find can, magenta, and then yellow. So can be found by having the mixing into the equal amounts for the blue and green. 50% blue and 50% green if you have, you will get the can. Similar is the case for the magenta and that of the yellow color here. Now these illustrations we can also have in this particular visualizations. So these three corners are representing R, G and B. We can have just rotation of the same model, and the other three vertices of this particular cube here are nothing but C, M and Y. So for a cube there are total 8 vertices. Okay, so 4 top corners and 4 bottom corners. So 3 of them are the designations of red, green, blue, RGB. Next 3 are CMY, can, magenta and yellow, and the 2 here you see that it is shown with the help of white color, and here it is shown with the help of black color. So whatever the grayscale image processing you had been learning thereupon, so it is on to just a line that is joining these two corners of this particular cubes here. So here it is the diagonal joining, here it is the diagonal of the particular cube here. So this is also known to be the grayscale level or the intensity axis here. So from the complete darkness you are going towards a complete whiteness here. So I hope these particular color terms, either you talk about the red, green and blue, and then further the can, magenta and yellow, and the complete black, complete white here. Some more illustrations also can be shown to you with the help of these particular diagrams here. You see the different shades as just now talked here, and the different corners are of course shown with the help of the same color. So for the yellow we have shown it with the help of the yellow, red color and the same here. And here it is what the combinations of the pigments or the colors you see that is producing either the black or the white here. Here it is at the central level black color here, or this particular illustration will be the most useful to you people. These are the primary colors you see. Here it is the red, green and the blue here. When you combine the red with blue, it will create magenta. See here, mathematically also we have shown to you, red plus blue, it will create the magenta. Or another way it is there, from the white portion if you subtract the green component, so here it is the expression, that also will give you the magenta. For the can, what will be you do, you will have the addition of the blue color with that of the green color, that will create the can. And another way is to have just the subtraction of the red component from the white. Next, for obtaining the yellow, you will have to add the red with the green, it will give you yellow. Or another thing is you just subtract the blue component from the white, it will also give you the yellow color here. So this is what all the information I have shared with you people to describe the CMY color model and shift to CMYK color model here. And it is quite interesting when you work on to the fundamentals of this particular color image processing, pseudo color image processing with the help of any of the image processing tool. So the practicals will be really giving you a sound knowledge of this particular field that you can apply in your career here. So I hope the things are very clear to you people. You can attend my all other lectures also, or you can find the various details. I have already made it online on Ekeeda platform. The practicals are also there included. You can attend them, you can practice hands-on to get a complete clarity of the concepts and a practice here. So thank you. We shall meet you into the next session by the next week with another topic from the same subject here, image processing. The topic it will be image pyramids here.